Morning, everyone. So let me remind you, in the last 3 lectures, we sort of set the stage for discussing fun IR aspects of gravity. In the first lecture, we discussed basics of flat space and asymptotic flat space and introduced a framework that allows us to discuss very naturally the boundary of asymptotically flat space-times. Then yesterday, in the 2 lectures, we discussed various infrared aspects of gravity, which a priori seem completely disconnected, which were, on the first hand, asymptotic symmetries, then soft theorems, and memory effects. And those 3 turn out to be intricately related. And they gave us some motivation to look for a putative holographic dual to quantum gravity in asymptotical flat space. So in today's lecture, we're going to discuss what those words mean. So let me call this So this is the 5th topic that we're going to discuss. And let me start by telling you what this title means. So I'm again going to draw the Penrose diagram of asymptotical flat space. You remember that at every point here, there's a sphere. For the most part, we are focusing on 4-dimensional asymptotical flat space. And then we have a 2-dimensional sphere, which at the boundary is referred to as celestial sphere. And the statement of this title here is a proposal that says that quantum gravity in 4-dimensional asymptotically flat spacetimes is potentially dual to a theory which I will refer to as celestial conformal field theory with quotation marks on the celestial sphere. So this is the idea that we're going to discuss today. And the reason why I put the right-hand side in quotation marks is that we don't yet know what this theory actually is. So what we're going to see in today's lecture is that certain aspects of physics, of bulk physics, looks like a conformal field theory on the celestial sphere. But there are also rather exotic-looking features, which is why I've put the word celestial in front. So this is not your ordinary vanilla conformal field theory that you find in Di Francesco. And it has quotation marks here because we're still exploring and trying to find out what this theory actually is. So this celestial sphere here lives at the null boundary of asymptotical flat spacetime. And we're going to discuss properties of bulk quantities when recast in a certain way that will kind of give us a flavor of looking like there's a conformal structure, conformal field theory. So what's the motivation for this? So the first motivation for this proposal is by looking at symmetries. So I told you yesterday, I mentioned that the Lorentz group in 4 dimensions acts on the celestial sphere at the boundary as the global conformal group. Who knows about this? Okay. Let me propose the following. So we have a Q&A session. I can tell you a little bit about how you see this, how the generators of the Lorentz group in 4 dimensions map onto the generators in 2 dimensions. Does that sound good? And we're going to take this as a given for now, because it's, math and algebra. Okay? And furthermore, let me actually write it as this. So capital D is the spacetime dimension, and let me say this is D plus 2, because we have chosen here our D dimension to be 2. And this statement actually holds in general. So if you have capital D bulk dimensions, there is a codimension 2 sphere, so it has D dimensions, little d dimensions, and then the Lorentz group in little d plus 2 dimensions acts as the global conformal group in little d dimensions. Okay, so that's the first motivation for why there could be some conformal field theory living on the 2 sphere, is because we have the global conformal symmetry there, because of Lorentz symmetry in the bulk. Now, the second motivation comes from looking at observables. So, okay. What's the natural observable in flat space? S matrix. So let's discuss the S matrix and how it helps us to see that there may be some conformal structure at the boundary. So let me again draw the Penrose diagram. So let's say we consider massless particles for simplicity. They come in from the past. Then there's some fun scattering event that takes place. And then they go out to the future. Usually, in the context of massless particles, massless particles we label by their momenta. We discussed yesterday that there are 3 labels, the energy scale and then the direction. So I'm gonna again use omega as the energy and then little x for the direction. So that's a point on the sphere where the massless particles is traveling to. And well, you see, we are usually discussing scattering on the S matrix in quantum field theory in an energy basis or energy momentum basis. And, well, actually, I need some space here. And so your standard amplitude is just expressed in terms of, let me get some notation here, in terms of some in and out momenta. Well, let me say 1 to n, so 1 to n particles, some are in, some are out. And this is your standard. Let me refer to this as standard amplitude from now on. And what does this make manifest? What kind of symmetry does it make manifest? Translations. So we work in an energy momentum basis. The amplitudes have a Dirac delta with momentum conservation, so it makes translation symmetry manifest. Now, it turns out that that is not the most useful observable for discussing holographic properties of quantum gravity in asymptotic flat space. So what are we going to do? So we hinted at this yesterday, and it's the reason why I emphasized that this is making translation symmetry manifest. If you look at the first item here, what does it suggest to you that we should do? So I said Lorentz symmetry in the bulk looks like global conformal symmetry on the boundary. Our standard way of writing down amplitudes makes translation symmetry manifest, so what should we do? I didn't hear anything. Yeah, we should maybe change the basis that makes manifest the symmetry that gives us global conformal symmetry on the celestial sphere. So let's do that. So how is that done? So we need some transform. So we already encountered the transform yesterday when we discussed the connection between well, we didn't discuss it in detail, but memory effects and soft theorems are related. We discussed how asymptotic symmetry and memory effects are related, and we discussed how asymptotic symmetries and soft theorems are related. And then I told you that memory effects and soft theorems are related by a Fourier transform. Well, if we do a Fourier transform here, we go to position space. That's not the convenient basis for discussing holographic properties. But there's another transform. And this transform is called a Mellin transform. And what it does is it takes the energies of all the external particles in your amplitude and integrates over them from 0 to infinity. And then rather than having this exponential as in the Fourier transform, we have the energy to some power, and let me call that power delta, delta minus 1. And we will see in a second what delta is. So what that means is we trade energy for this delta, and our massless particles, which were originally characterized by this omega and by a point on the sphere, are now described by this delta and a point on the sphere. So what we're doing is we're trying to make manifest conformal structure on the sphere. So we want to have some object here, our S matrix, that is an object that intrinsically lives on the two-dimensional sphere, or a d-dimensional sphere. And the way to do this is by integrating all of the external momenta from 0 to infinity in the energy and spitting out this other parameter, the dual variable delta. Yeah. X is, so this would be, for example, the angles theta phi. So that was the X that we had yesterday. I put an A yesterday here. Here I'm like lightness of notation. And I for, because we have like a couple of particles that we put into that we stick into our scattering process. Now it turns out that when you do this basis change, what will happen to your standard amplitude is that it will look like an object that lives on the celestial sphere, which is characterized by where you insert the objects in the amplitude. So every particle here that takes place in this, that takes part in the scattering process, will be mapped or will be characterized by an operator that you insert on the celestial sphere. And the amplitude will turn into something that looks like a correlation function on the sphere. So each of these operators, 1 to n, will correspond to some operator insertion at all these points, x1 to n. It will be labeled by this new parameter delta rather than the energy from 1 to n. And then the information about whether the particle was incoming or outgoing will translate into a label of this operator. Let me call it minus and plus. And so here these are the like x1, xn. Those are the points on the celestial sphere. Let's say the dimensional sphere in general. And this is what happens to your amplitude. So these operators will be labeled by delta, and we will derive in the following that this delta corresponds to nothing other than the quantum number of the global conformal group on the celestial sphere, so the conformal dimension. So there is the particles, there are particles that are incoming and the particles that are outgoing, and that translates into a label, because here there is no, this is just a correlation function, and the minus and plus tells you about whether this is a dot or an X. Okay? Yeah? So so here I started with there was a particle P1 that was incoming, which translates to an operator, which instead of having omega 1 has delta 1. The information in the P had also X, so that stays the same, that doesn't change. The in turns into the minus. So that's how the energy momentum basis particle notion translates into this correlator. I'm not deriving things here, I'm motivating things. We're gonna derive stuff in a moment, but I'm giving you the broad brush picture to give you, some motivation or some idea what's gonna happen in the following. I don't know if this answered your question. Yes? So you can write on a 2-point function here, which will give you a 3-dimensional delta function in the 3 momenta. And that has a corresponding statement after you do this Mellin transform. If you take P1 and P2, then there's a delta that sets equal the omegas and the 3 momenta here. Yeah. So no, I'm not doing any averaging. So what I'm doing is this integral transform. So I could have said, okay, let's take our amplitude, there are momenta in there, I do the Fourier transform, then I get something in terms of x's. Now what I'm doing is I'm not transforming all all the entries in my P vector. So in Fourier transform, if you can transform the 4 vector and you just get position space variables, no momentum. What I'm doing now is I'm gonna take, so for massless particles, I wrote the momentum in terms of the energy and a point on the sphere. And I'm just transforming the energy. I'm leaving the point on the sphere as is. Okay? Well, we're gonna get to all the details now. So this is, let me give you the motivation, and we're gonna derive how the asymptotic states that we stuck in here become different asymptotic states after this transform. We're gonna do this in a second. So this is the broad brush picture. Your standard S matrix in the energy momentum basis, once you do a Mellin transform on all the external particles, Mellin transform in the energy, it turns into an object that looks like a correlation function on the codimension 2 sphere. And the label that you obtained by integrating over the energies corresponds to the conformal dimension of these operators, so that labels that. And we're gonna derive why this is the conformal dimension in a moment. This is just to motivate things. So we can call this conformal dimension, or we can call this boost weight, because it comes, or the global conformal symmetry comes from Lorentz symmetry in the bulk, and there is a generator of the Lorentz symmetry in the bulk, let's say the boost in the 3 direction, which will map onto the conformal dimension here. So let me call this boost basis. We can call it conformal basis. And so here I'm telling you that once you do this transform, then you get a correlation function in something that looks, well, something that looks like a correlation function in a conformal field theory. But let me mention some, and because of this, because you have made manifest global conformal symmetry on the sphere, it means that we have now made Lorentz symmetry manifest. So this is what this change of basis did for you. Rather than having translations manifest, Lorentz symmetry becomes manifest. And we will see how translations still arise, but they arise in some funny looking way from the perspective of ordinary conformal field theories. Okay, before telling you what's weird about this, let me say one more thing. So, okay, let me explicitly write this down. So we have global conformal symmetry. And we're gonna see, so okay, global conformal symmetry is nice. We can organize things in a different way. We can reshuffle the S matrix and look at it from through a different lens. But that's not good enough if you want to have holography. So if you want to have a CFD, and in particular if we are interested in our world, which seems to be 4-dimensional, where the sphere is 2-dimensional, then this is not good enough. Why is that? We would like to have local conformal symmetry, so we would like to have local standing here. How do we get that? Can anyone guess how this is gonna come about? Okay, I heard some words, but I can't distinguish them. So Lorentz symmetry gives us global conformal symmetry. We want to enhance global conformal symmetry. Ah, super, okay, yeah, super is good. So we wanna enhance Lorentz transformations to super rotations, and it's super rotations that will then tell us that we have local conformal symmetry. Yeah?
Do you have any reason to expect that there should be local? Because then ordinarily we don't have that with a conserved stress tensor. We're looking at the boundary.
Yes. And I kind of spilled the words yesterday when talking about soft theorems. If you remember, the word stress tensor came up, and we're gonna get back to that today. So super rotations, that's the symmetry part of the triangle. That symmetry part of the triangle is related to a soft theorem. We discussed that yesterday. This was the subleading soft theorem, which, among other things, gave us angular momentum conservation. And it's that subleading soft theorem which will contain a stress tensor. So there will be we have written it down at the end of last lecture, but maybe it was a bit fast, so we're gonna write it down today again. The subleading soft graviton theorem, we have chosen a suitable parameterization for momenta that works at late times and large distance. So this was the weird stuff that it was doing at the end of the lecture, where you might have thought, okay, why are we using this like technical whatever? But that one let us write a Sublin-Soft theorem as something that looked like a water density, a two-dimensional water density. And by massaging it a little bit, it became clear that this looks like a water density for a stress tensor. And this is how a stress tensor will come about. It didn't quite work because we had an operator in there rather than, so there were no conformal weights in there. There was an operator in terms of the energy, which made it clear that energy is not a good basis to discuss this. And so what we're going to learn today is that once we go away from energy and replace it by boost weight or conformal dimension, that will make manifest that the sublinear-soft graviton theorem is the correlation function of a stress tensor in a two-dimensional theory that looks like it has some conformal properties. So this is how this will come about. Okay. Oh yeah, I wanted to make some comments. So that was this here. Okay, let me make them here. So comments. So I said that we're going to get something that looks like a correlation function in a two-dimensional theory, or in a d-dimensional theory, if you wish. But there are some weird aspects. And one weird aspect comes from the fact that we have energy momentum conservation for the S matrix. And so there's a Dirac delta in the momenta. When we integrate over the external momenta, so long as we have enough particles in the process, which gives us enough integrals, we can eat up this Dirac delta. But for low point amplitudes, in particular for 3 and 4 point amplitudes, the four-dimensional Dirac delta will not be eaten up. There will be some remnant Dirac delta once we do this Mellon transform. So let's say we have a 3-point function here. We have a 4 momentum conservation, so there are 4 deltas. So if we integrate over, there will be deltas left. And so this correlation function here will only have a part that looks like an ordinary correlator, and then it will have a part that has Dirac deltas. So for n equals 3 and 4, we'll have kinematic Dirac deltas, and these will be in the angle coordinates, let me call it Zij, which will denote from now on the difference of Zi minus Zj, so the difference between the insertion of these operators. And so that's for 3 points, and then for 4 points, we'll actually have kinematic deltas in the cross ratios. So we're gonna get to that maybe later. There's also Dirac deltas in the boost weights. So there's some overall Dirac delta that constrains the sum of all the boost weights. So let me write this down as there's a sum over all the boost weights, and potentially there's some number in there as well, which is related to how many particles are involved in the process. And so you have also a Dirac delta in that. And so these two things look rather peculiar from the point of view of ordinary correlation function in a CFD. So this is something to keep in mind, that there are some differences to ordinary correlation functions, but otherwise, the S matrix expressed in this boost basis shares some nice properties with correlation functions in a CFD. Okay, good. So that was sort of the broad brush picture of where we're gonna go. Now let me give you some more perspectives on this whole holographic picture of asymptotic flat space. So I've now discussed 3 bases for scattering, or introduced. So on the one hand, we studied objects in an energy basis. So that's what we did when we looked at soft theorems yesterday. On the other hand, we discussed objects in a position basis. So this is when we discussed the memory effect. And now I introduced yet another basis, which I hinted at yesterday, but it will become clear much more today. This is the basis that makes most manifest what the symmetries are. Now, you all know how to go from here to there. So this is a Fourier transform. I just introduced to you how to go between the omega and the delta basis. So that is this Mellin transform. Let me write it out again because it's probably not familiar to you. Okay? And then obviously there should be a way to go directly between delta and u. So either you do just a sequence of Fourier transform and Mellin transform, or you can see that this boils actually down to an integral. So let's say we go from u to delta. So this is going that way. So integral over u from minus infinity to plus infinity with a u to the minus delta, and then whatever is the object that you're transforming. Okay? Yep. Exactly. Thank you for asking this. This is my next point. So let's go in a pedestrian way from the bulk to the boundary. So this is what in ADS-CFD, there's a bulk to boundary dictionary. You have objects and things in the bulk, and you can map them to the boundary. Now let's start with the simple operator in the bulk. How do we take it to the boundary? So let's say in 4 dimensions, equals 4 bulk. And we look at some operator in the bulk at some point x. And what we want to do is we want to push this operator to the boundary. Okay, so let's say we want to study massless operators. So massless particles, we want to push this point to the null boundary. So there is some operator, let me call it O hat of x. And that's a bulk operator. Oh, I think I need more space. Let me go there. So we start here. What do we do to get to the null boundary? If we write this x in terms of u, r, z, z bar, r goes to infinity, that's the first thing that we do. Then, okay, we can discuss different objects. We can discuss scalar or spin 1, spin 2 objects here. If we want to have something finite for these objects at the boundary, we should also multiply them by some power of r when we take r to infinity. So you can, if you have a scalar and you look at the mode expansion of a scalar, free scalar, and you push it to the boundary, so you take the large r limit, in the mode expansion there will be some exponential with ik dot x. If you write the x in u and r coordinates, there will be some e to the I omega r terms there. So if you take r to infinity, there will be some rapid oscillations, and I mentioned this yesterday. In order to push this operator to the boundary, you can do a saddle point approximation. And we wrote down what the saddle point is. And in doing so, the scalar will have some particular fall off in R. And it will, in particular, fall off like 1 over R. So in order to have something finite, I'm just going to multiply here by R to the 1 minus S, where S is the spin. So this is just 1 power of R, and that gives me some finite object on the boundary. So that S is the 4D spin. For gauge fields, if you do the same thing for gauge field, you write down the mode expansion of a free Maxwell gauge field. You push it to the boundary, you will see that the angular component is already a constant, so that means 1 minus 1 is 0, so you don't have to do anything. If you look at the graviton, so if you take a free graviton field and you push it to the boundary, there will be an order r term, which is the shear. Remember, the metric is some r squared times the sphere plus r times the shear. So the shear will be the thing that is finite at the boundary, and I have to multiply by 1 minus s, which becomes 1 over r. So that kills the r from the that's standing in front of the shear. Okay, so what happens when we go to the boundary? Well, what boundary? So we're taking R to infinity, so we're gonna go to that whole codimension 1 boundary, okay? So let me maybe write it like this. So we have a 4D bulk. Once we go take R to infinity, we get the 3D boundary, null boundary. And we talked about yesterday what some characteristics of this null boundary. There was this Carolian structure which said that the induced metric on the boundary is degenerate, and then there's a normal which is given by d by du. So this is u and this is v, if you don't remember. Or on the path boundary, it would be d by dv. And I told you also yesterday that the physics on null boundaries is rather weird, and you could think of starting with some quantum field here and taking the speed of light to 0 limit to discuss the physics there. And that will give you some Carolian theory. And there's an active research program that tries to make sense of Carolian conformal field theories, trying to find actions that when you quantize them make sense and give you something that could potentially be a holographic dual to quantum gravity in the bulk. So there's a whole research program about that. I was starting out telling you about celestial holography, which is just talking about the sphere, not the whole null boundary. So what's happening? So in order to go from the 3D boundary to just the celestial sphere, we should get rid of the retarded time direction, or the advanced time direction, right? And this we can do by integrating over that direction, so minus infinity to plus infinity du, in a certain way. And it's that way that I wrote upstairs. So if you integrate the object that lives on a 3D null boundary in this way over u, then you will get rid of the retarded time direction, and you will land on just the two-dimensional celestial sphere. No. And the theory that we're going to call this theory, as I said, celestial conformal field theory, as opposed to Carolian conformal field theory. So there's an unfortunate clash of C's. So here we refer to this as CCFD. I guess we were first in giving this short name. And then this is called, I think that's what it's called. So, yeah. But these two are related in this way. And you could also go backwards and integrate over delta to get back to u. So you do the inverse transform to go from physics on the 2D celestial sphere to physics on the 3D Carolian boundary. So we're going to skip that Carolian part, and we're going to go straight from the operator in the bulk by taking this large R limit and taking this light ray transform, which is this object. It's a light ray, right? So you're doing a light ray transform. And we're going to go from a 4D operator in the bulk, at the bulk point capital X, to an operator on that's inserted at the point little x on the celestial sphere. So the picture that I had there was the full space-time Penrose diagram with a point in the bulk. Once I've pushed this to the boundary, the picture here will be that there's a celestial sphere, and I insert an operator at the point little x, S2 or SD. And this is an intrinsic boundary object. Okay? So this maybe answers the question of Carolian celestial. And these are two sort of research programs that go in parallel. And depending on what question you ask, either one of them may be more suitable. Okay? So what I think is more suitable for discussing the symmetries of quantum gravity is this piece. And we have found a lot of results that would have been very hard to imagine that one can find them in the original energy momentum basis. So this was one of the big boosts that the flat space holography program got by looking at how symmetries arise when you make Lorentz symmetry manifest and you work on a theory on the celestial sphere. Okay. So much for motivating what this picture is about. Question? Yeah.
Are there any criteria to compute the value of delta?
Okay, very good. We're going to get there. So let me introduce the basic building blocks of what we refer to as celestial conformal field theory, and then let's talk about what delta is. Okay? Okay, so CCFD building blocks. So here we talked about sticking in plane waves to get our amplitude, and which made translation symmetry manifest. Now we want to find the objects that we have to stick into our S matrix such that we get this correlation function form and make Lorentz symmetry manifest. So let's look at how we describe asymptotic states. And let's start with the massless case. So we discussed we should stick plane waves into our S matrix. So let me call this phi omega, to denote that we are on the energy momentum basis. And let me denote whether we're talking about ingoing or outgoing states by a plus minus here. So there is an e to the I p dot x, p is the momenta, x is this capital X from before, where this p here, p mu, is omega q mu, and there's a plus minus, let me write this bigger, there's a plus minus keeping track of whether we're talking about ingoing or outgoing particles. And this q here, from now on, because I'm working now, from now on the celestial sphere, and it's very convenient to work with complex coordinates, I'm gonna go back to the z and z bar that we introduced yesterday. So then let me write this out a bit more. So this is e to the plus minus I omega q dot x. And now what we're supposed to do is we're supposed to take this Mellin transform. That's what we learned above. So we integrate from 0 to infinity over omega. And you can do that. That's an easy calculation. What you find is the following. There's some normalization factors. There's a gamma function here. But the important piece is the denominator. So there will be a minus q dot x to some power delta. You can easily see this by remembering what the integral representation of the gamma function is, and then working your way backwards to land back on the exponential here. So let me give this a name. So let me call this capital phi delta. I put the minus plus here, which comes from the plus minus from the in and out. But actually, this integral transform is not well defined everywhere. So in order to make it well defined everywhere, I have to put a little epsilon here, epsilon omega here to make that well defined. And what this does on the right-hand side is it shifts this denominator a little bit. Let me call this plus minus. So this just means that inside this inner product q dot x, there is also a plus or minus with the epsilon. So in particular, that will be a plus minus I epsilon in this denominator, so that I avoid the zeros of this quantity. So this is just to make this, so all these plus minuses are keeping track of in and out, and they make this transform well defined and avoid the zeros of the denominator here. So these were plane waves. And after the Mellin transform, we get objects that depend on delta rather than omega. And they also have a name. So we refer to them as conformal primary wave functions. And we're going to now see why, where the name comes from. Okay? So they're called conformal primary wave functions because phi delta transforms in a certain way under transformations of the, okay, let me explicitly write the dependence here. So there's a dependence. This object depends on capital X, but it also depends on this Q. So So remember there's this Q here, which depends on Z and Z bar. So not only do these wave functions depend on capital X, the bulk point, but they also depend on the direction of where the object is going. And that's the point on the sphere. So this depends on capital X, and I could either say little x, because that's what I called it before, but little x from now on will be Z bar. Okay, so this object transforms in a certain way under the following transformations. So there is a bulk Lorentz transformation of x. So x mu goes to lambda mu nu, x nu. And there's a boundary transformation on the little x, or the z, which takes z and z bar to z prime and z bar prime. And you may now be able to guess what kind of transformation I should write down here, because we said we have Lorentz symmetry in the bulk, which becomes global conformal symmetry on the boundary. So you can guess what kind of transformation I should write down here. I should write down the conformal transformation, or Möbius transformation here. So Z goes to Z prime, which is AZ plus B over CZ plus D. And then the same for the complex conjugate. Everything barred. So remember, this is the Möbius transformation. And it has A, B, C, D, as well as the barred ones, complex numbers, with the condition that AD minus BC is 1. Okay? And so the statement is that when you take this conformal primary wave function, the thing that I've written up there, you do a bulk Lorentz transformation, a boundary Möbius transformation, then this object transforms under these as a two-dimensional conformal primary, which means phi delta, I'm dropping the plus minus here now since it's not important for this statement. So once you have transformed x and z bar, then this will look like the following. Del z prime over del z to the power, absolute value to the power minus delta, phi delta of x mu z bar. And this term here, when you go through that computation, will be equal to Cz plus D, absolute value, to the power 2 delta. So this is an exercise that I leave you with. Take this wave function, do a combined bulk and boundary transformation as so, and you should find that it transforms in this way. So you will find this object, which you can rewrite as this. And once you see this should ring a bell if you have taken a 2D conformal field theory class. This is the transformation of a two-dimensional conformal primary. So we have a four-dimensional bulk wave function which transforms as a two-dimensional conformal primary on the boundary 2 sphere. Yeah? So if you forget about the x dependence, that's kind of ordinary, two-dimensional conformal primary, but it also has an x dependence, it's a wave function, right? Yes?
Why is there no Z bar on the transformation?
Oh, because there's an absolute value. There is a Z bar. And also here, these are absolute values. So absolute value squared is just, so what this means, this is just this. Okay? Okay, great. So we have introduced a very basic object, a scalar wave function, which, from the point of view of this two-dimensional celestial CFT, is a two-dimensional primary, conformal primary. Since I mentioned that in the Q&A session, I can go into a bit more detail of how 4D Lorentz symmetry and 2D global conformal symmetry are related. I will, if you're interested in that, we're going to discuss then in a little bit more detail how this comes about. Okay, but yeah? Oh, that's a good question. Let's get there. Let's do massive. Thank you. So for massive particles, the story is a bit different because it's not just an energy label and a point, and so it's not good enough to just get rid of the energy. A massive particle doesn't go to null infinity naturally, so it's not a natural object there. It goes to time like infinity, right? So things are a bit different there. So instead of trying to find directly a transform that makes us have a massive wave function look like some nice object from the 2D CFT point of view, let's sort of engineer it backwards. So one thing that is satisfied by these massless conformal primary wave functions, obviously, because they did so in the plane wave basis, is that they satisfy the massless Klein-Gordon equation, right? So phi delta, so this phi delta here satisfies the massless Klein-Gordon equation. So box phi delta equals 0. Those are the two characteristics. You satisfy the wave equation, well, the equation of motion for the particle of that spin, so massless and spin 0 in this case, and you have this transformation property as a conformal primary. Now let's go to massive. So for massive, what do we have to satisfy? Well, the massive Klein-Gordon equation, right? So we're gonna make an ansatz for a putative object phi delta m. So we don't know it yet, so this was the massless one. This is how I'm gonna label the massive one. We wanna find an object that satisfies box minus m square is 0. And it should be an object that depends on delta. Let me make a comment here. So in ADS-CFT, the conformal dimension of the object and the mass is related. But this is not the case here. We're going to see what the range of delta is. There was a question before that in a moment. But these are just two different labels of this field, okay? So the mass and the dimension are not related. Now let's make an ansatz for how this should look like. A good guess might be that we should have a structure like this, 1 over q dot x to the delta. So let's start with that. Minus q dot x to the delta. And from in between, I will drop these plus minus labels. So there was a plus minus label here. I will drop them when it's not important, and I will put them back in when it's crucial. Okay, so we may end up with a structure like this, but then there could be a function upstairs that we have to specify or like find when solving this equation. And the question is, what can this function depend on? So this is a scalar, so it should transform a scalar under Lorentz transformations. So there's not much dependence that I can write down. The thing I can write down is x squared, right? It's a Lorentz scalar, so that's what I can write down. So this is my ansatz that, well, let's say this is proportional. So this is my ansatz for a massive conformal primary wave function. And I now have to see if that satisfies the massive Klein-Gordon equation. I'm going to leave this to you as an exercise. And I'm going to give you the solution. So the solution for this f here. So you figure out this f by solving the Klein-Gordon equation. And what you will find is that your massive wave function will go as follows. So there will be an x square with some rational powers. And then there will be the minus q dot x to the power delta. But there will not be only x squared with some powers, but there will also be a function of x squared. And this function turns out to be a modified Bessel function. with argument m square root x squared. So this is the modified Bessel. So the way this comes about is that in trying to solve the Klein-Gordon equation, you will find a Bessel function of the first kind, and then you have to figure out, kind of like you did yesterday in these lectures, what kind of solution, what kind of combination you have to keep. So you have to keep something that makes sense if you go to large distances, and this will land you on the modified Bessel function here. Oh. Yeah, so the principle here was that I don't know what is the generalization of this Mellin transform for massive particles yet. If I know a bit of ADS-CFT, I can figure that out, and I'm going to mention that in a second. But if I don't, what is the first thing you do? Well, here we have an object that satisfies the massless Klein-Gordon equation. Let me just find an object, try to find an object that satisfies the massive Klein-Gordon equation. And now you have to make an ansatz. The ansatz was, well, let's borrow what we learned about the massless case. So there was this 1 over q dot x dot delta. Let me start with that. And then I have some free function. But the free function, since I have a scalar, it has to also be a scalar on the Lorentz transformation. So the only dependence I can write down here is x squared. So this is some function of x squared which you have to determine. Okay? And you do that, and you determine that it's this Bessel function. Sure. This is the bulk massive Klein-Gordon equation. So remember what we're doing in this, to some extent you could say in this celestial holography program, is we're trying to understand the S matrix in a new basis. But we still have our usual bulk physics. We have everything that is there in the bulk in the energy momentum basis, but once we translate it, it may arise in the boost basis in some more obscure way than what we're used to. But we still have the same bulk physics. So in this, this is a bulk wave function. This depends on the bulk point x. But now instead of having the energy in there, we split the momentum into like energy and point on the sphere in the massless case. And then we transform the energy to delta. Now here I haven't told you what we'll transform, but you know that the object has to contain the direction and it has to contain the bulk point. So this was the ansatz here. And the mass is the mass of your 4D field. Now you can also take the massless limit of this. So you take m to 0. And what you should then land on is just 1 over minus q dot x to the power delta. And that's exactly what we got before. And in this ansatz, I have dropped the normalization factor. Okay? Now, let me just tell you this in words, or like maybe let me write it down here. We will not spend too much time with massive particles because they're much more complicated than massless ones from the point of view of celestial conformal field theory, and they are much less explored. So if there's something that you want to make progress on, this would be a topic in flat space holography where there hasn't been too much work yet. So there may still be some low-hanging fruit lying around or hanging around that you might be able to pick. So now we have constructed a massive wave function, and you can check that it transforms as a conformal primary. So again, you do this transformation of the bulk point and the boundary point, and you should find that this massive conformal primary also transforms with dimension delta under global conformal transformations, or this combination of bulk and boundary transformations. Okay, so there is a transform that takes you naturally to this object, and let me just write it down. We're not going to discuss it much more, so I'm putting the plus minus back in to be complete. So what happens in the massive case is that objects want to go to the future time-like boundary, right? And we discussed yesterday, or the day before, that a natural way to discuss the physics near a time-like boundary is to, well, we first have to blow it up. It's a point here in this diagram. And a natural way was to introduce this hyperbolic or Euclidean ADS3 slices here. And these slices are taken to infinity by taking this label here, tau, did we call it, to infinity. Now, in order to discuss massive wave functions on the celestial sphere, what we should do is we should take these massive particles and exploit this slicing here. What that means is that there are, from ADS-CFT, if you're familiar with that, you can relate bulk and boundary objects by what is called a bulk-to-boundary propagator. And this is kind of what we're doing here. So there's this Euclidean ADS3 slices, and there's bulk-to-boundary propagators that allows us to write this massive conformal primary wave functions, or massive object, in celestial conformal field theory. And the integral transform that you should do is, well, it should be 1 over this hyperbolic 3 space. Massive particles, they are labeled by their 3 momenta. The head just indicates that I'm dropping various 2 pi's and so on here. And then this G is the Euclidean ADS3 bulk-to-boundary propagator. It depends on the momenta of each of these particles, and then our boundary point Q, and then there's also an e to the, now there's the mass in there, I am p hat dot x. So that replaces the I omega q dot x, and instead of having just the I omega q dot x with this, okay, we lost it, so 0 to infinity, the omega to the delta minus 1 was for the massless case. Now this looks a bit more complicated. Yeah.
So if you're taking the Riemann transform of S matrix for your shells, how do you end up with actually some massive variable on the non-infinity?
So we're not doing, for the massive particles, we're not doing a Mellin transform. For the massive particles, we have to do that transform with the bulk-to-boundary propagator. Yeah. Yeah. So since this is more complicated and would take much more blackboard space to discuss any of this, we're not going to do it. I can give you some references where some stuff is discussed, but it's not too well explored. And the reason is that there's a lot of things that are very basic that we have to explore for the masses case, and to get even basic questions about symmetry right. And so this is what most focus has been on. Yeah, but I wanted to give you that because often there's often a misconception that celestial holography is only about massless particles, and that's not the case. We just have so much to do and to learn about the massless case that we haven't even gotten really to explore much about the massive case. But there's much to be said about that too. Okay, so I think I'm supposed to give you a break. Let me say one more thing and then we're gonna do a break. And the thing is, so for now we have discussed massless and massive scalars. What about spin, right? We talked about gravity the whole time. Yeah? We need to say something about gravity from the point of view of celestial CFT as well. So let me now introduce massless spin S particles. So we have learned now a little bit about how conformal primaries look like. So they have to satisfy some equations of motion, and they have to transform as 2D conformal primaries. So let me give a definition of a conformal primary wave function of spin S. So we have already our label delta. Now let me add a label S for the spin, and I'm gonna put back the plus minus here. These objects depend on a bulk point and a boundary point. Let me call it little x, which is z bar. And for massless particles, we're going to talk about helicity. So there are 2 polarizations for the photon and for the graviton. So this S will just be the absolute value of the spin. And then in 2 dimensions, I'm going to write a 2-dimensional spin, which will be identified with the 4-dimensional helicity. So if we're looking at spin 1 particles, the J here can be either plus or minus 1. And similar for spin 2, we can have either plus or minus 2. Okay? And the definition of these objects is now that, okay, as written here, there should be a function of x, of capital X, the bulk point, a function of the boundary point. We wanted to solve the linearized equations of motion, and I'm saying that because for gravity, we would look at the linearized Einstein equations. So linearized spin S equations of motion. Let's say the things that we're most interested is Klein-Gordon, Maxwell, and Einstein, linearized gravity. And they should transform under x goes to lambda x and z goes to az plus b over cz plus d as follows. I'm going to get all these labels there. I'm going to drop now the plus minus. So they should transform in the following way. So there was this, for the scalar, we had cc plus d with absolute values. But now we have spinning objects potentially. So there will be a spin involved here. So the first one will be cz plus d to the delta plus j. And the second factor will be c bar, z bar plus d bar to the delta minus j. Then if we have spin, some bulk spin, there will be indices here, Lorentz indices. So I also have to transform those, and I will denote this by ds. So this will be the spin S representative of the Lorentz algebra. So how the bulk spin transforms, I have to do that. So this depends on lambda. And then I have the untransformed object, x and zz bar. Yeah, so I'm making this distinction for two reasons. First, S will be just for me like whether it's spin 1, spin 2, spin 0, and J will also have the sign in there, whether it's plus or minus 1, plus or minus 2. And after the break, we're also gonna discuss cases where the bulk spin S, what I call S here, is not the same as the 2D boundary spin J. So we're gonna discuss an example there. Yeah, here I mean conformal primary wave function. Okay. Yeah. It's global primary, exactly, under the global conformal group. We have not done the enhancement to local yet. Okay, and now let me just write down the examples. So spin S equals 0, we had this object that looked like minus q dot x to the power delta, with a plus minus if you wish. And so let me drop the normalization factor that I had in the beginning, which involved the gamma function, and let me call this little phi delta. So this is our spin 0 conformal primary wave function. Now, spin bigger than 0, what would you have to do? So if I give you a plane wave, how do you get spinning wave functions? What? Yeah, I need some polarization, right? The rest with polarization vectors, potences. And I'm going to use the one that I already wrote down yesterday, but I'm going to write this in a different form. So this should be normalized in some way, which is why I put the 1 over square root 2. And then we're going to use this, this vector q, this null vector q, which points to a point on the sphere. And what I denote now, well, I guess I called it capital A before. Well, in the future, I might call it little a, so this is what you find in the literature. Little a just means plus minus, depending, this will give you the polarization of whether it's positive or negative helicity. So this is plus or minus. Let me write it in this way, plus or minus. And on the right-hand side, the way to get plus or minus polarization is by taking a z or z bar derivative of this null vector. So this denotes z or z bar. So this vector that I wrote down yesterday towards the end, if you take z or z bar derivatives, you get polarization vectors. Now the thing is that if you take this polarization vector and you look at how it transforms on the conformal transformations, it doesn't transform nicely. But we want a spinning object that does transform nicely. So we have to do something to that guy. And so a polarization vector that transforms nicely is by taking a combination of these epsilon polarization vectors and shifting them in such a way that the object that you obtain is actually transforming nicely under Möbius transformations. And so this is done by these two vectors in a natural way. So this is the inner product between epsilon and x. And as an exercise, you can check that these objects so that this object transforms with a conformal dimension 0 and spin +1. Let me write it like that. So delta is 0 and j is +1. And this guy transforms as delta equals 0 and j equals -1. So you just do the same thing as here, but for these polarization vectors. And that then gives you naturally a spin 1 conformal primary. So A with a label delta, a spin j. Let me focus on the +1. And then there is an index mu. So this has a bit of a lot of labels. Let me maybe drop the Lorentz vector label. Okay, so there's a mu index there. Don't forget it. And I'm writing this in terms of a polarization vector. I'm also going to drop that mu index. So there's this polarization vector that already has spin 1. It has dimension 0, so what object should I add here such that this becomes a spin 1 conformal primary wave function with some dimension delta? So right now this would be a wave function with dimension 0. How do I get one with dimension delta? Any guess? The Taylor wave function, yes. So there was this guy which had dimension delta. So delta is delta, and j equals 0, right? So I multiply this object here. And then I can also write a spin 2 conformal primary wave function, h delta, and let me focus on spin equals +2. How do I build that? I'm dropping the mu nu indexes here as well. How can I build a spin 2 wave function from what I discussed? 2m's. That's a good idea. That gives me the indices that I need, mu and nu. What else? Sorry? Well, m and m are the same, so it's symmetrized. But yeah, good point. What? Exactly, so I could have the opposite. So if I have j equals -2, I would use the barred one. I'm doing the one with the plus, yes. And then I want delta here, not 0. So, okay. So this guy gives you dimension delta. It has spin 0, and this guy gives you spin 2. You just add up those 2's. Okay? And if you want the opposite helicity here, you put bars. And that's it. So we constructed spinning conformal primary wave functions quite easily by just exploiting what the building blocks are. This one, it should be automatically traceless. Yeah. Okay, I think we need a break now. Let's say 5 minutes. You're still fresh, it's the morning. 5 minutes? Good. Okay. So before the break, we discussed massless and massive particles, how they can look like something transforming under the global conformal group with definite formal dimension and spin. In the end, we want to, so this sort of fits well with trying to understand the S matrix, looking at it through a different lens, the lens where Lorentz symmetry becomes manifest rather than translation symmetry. And this lets us ask questions that are maybe obscured in the energy momentum basis. Now, at the end of the day, ultimately the end goal would be not just to recast the S matrix in a different way, but to actually have a holographic dual to quantum gravity in the bulk. And so one of the things that you need to sort of understand really quantum gravity in the bulk is you need to also understand non-trivial backgrounds. You need to understand non-perturbative physics. And this is one of the big open questions in this program. How do you discuss like non-trivial, non-perturbative bulk physics? So this is still a long way to go, but let me give you like a little tiny step in that direction, and let me tell you how to describe from the celestial sphere boundary point of view one of the very simple background that you're probably all familiar with from your GR course. And this is a shock wave solution, okay? Shock waves are kind of like massless particles going to null infinity. So this is something that should be naturally describable by the tools that I have just written down. And indeed there are. So before we solved the Klein-Gordon equation with 0 on the right-hand side, now we can put a source on the right-hand side. So we add a source such that box phi looks something like this. So there's some integration over some parameter, and then there's a 4-dimensional Dirac delta for this parameter. And now solving that equation, so that's a scalar, the phi, gives me the following solution. So there's a logarithm in x squared, and then there's a Dirac delta in q dot x. And I will refer this as a scalar shock wave. You can then go and look at the transformation properties of this object, and you will find that it has dimension 1, spin 0, and this comes from a spin 0 massless particle. We can then dress this by polarization vectors. Before we talked about these m's, but I could also just add the factor of q, because that also transforms nicely on the global conformal transformations. I could add a factor of q here to this phi shock. And what this will become, well, on the right-hand side, I have to write a spin 1 object because of that index mu. Let me call that a mu shock. And you can convince yourself that this has dimension 0 and spin 0, and it comes from looking at a spin 1 object, because this has one index here. So this is kind of what I was referring to before. I labeled these conformal primary wave functions by a bulk spin, and then I have this 2D boundary spin, and you see like an example here that they can be different. Now let me add 2 of these vectors q mu, q nu, by shock. Now I have a spin 2 wave function on the right-hand side. And again, you can look at what the dimensions and spin are. So this would be dimension -1 and spin 0, but it comes from a spin 2 object in the bulk. And this object you may have seen in your GR course. If you take a black hole, a Schwarzschild black hole, and you ultra boost it, you get a shockwave solution. So this here is nothing but the Eichelburg-Sechsel shockwave metric. But we have recast it in such a way that we can see that this is actually transforming as a conformal primary in the 2-dimensional conformal sphere. So this is a nice background in the sense that we can describe it by an object that is a conformal primary in our 2-dimensional conformal field theory. So maybe doesn't look very familiar to you, but if you take a metric g mu nu and write it as eta mu nu plus some h, then this is what you would find. This is how this matches to the solution that I've written down. So if you plug in this h mu nu shock that I had there in here, then this is the full space-time metric, which is describing an Eichelburg-Sechsel shock wave. And just a side comment, since I've written this as eta plus Newton constant times h, so it looks like I'm linearizing something here. But in fact, you may know that the shock wave, Eichelburg-Sechsel shock wave, is a solution to the exact Einstein equations. That's a fun fact about this solution. At some point on the first day, it came up that some of you are studying the double copy. Let me also mention a comment here. So this Eichelburg-Sechsel shock wave is one of the simplest sort of classical double copies of a spin 1 solution. So this solves Maxwell equations. And this is sort of the single copy of this scalar shock wave solution. To those of you who those words make sense, this is a side comment. In amplitudes, double copy means that there's a certain squaring going on, so some gauge theory squared objects become gravity objects. In the classical double copy, this is the words that comes in here as Kerr-Schild double copy. And so what that means is that you have some gravitational solution that has a piece that is some special vector called Kerr-Schild vector. and then a piece that is a spin 1, a solution to some gauge theory solution. In this case, it will be Maxwell theory, and this object is precisely this spin 1 wave function here. So this is just a side comment for those of you who are interested in that. And a nice feature about these shockwave solutions, recast here as conformal primaries, is that if you study scattering on top of these backgrounds rather than in flat space, then this pesky little issue that we have kinematic delta functions in the angle variables that came from energy momentum conservation, that goes away here. So if you do scattering on flat space, because of the energy momentum conserving delta function, you're left with Dirac deltas in the angle variables. But if you, instead of scattering on flat space, you scatter on a shockwave background, then you get rid of that. And sort of then this becomes nice CFD correlation functions that look like ordinary CFD correlators. Okay? So now I've talked a lot about wave functions, but in the beginning I told you that we want to take a bulk operator and map it to boundary operator. So let me just tell you how you can go from wave functions to boundary operators, okay? So let me write down a definition and then motivate why this is actually something that you can recognize just from your quantum field theory tools. So there's some I for some convention. I'm writing down brackets here, which denote an inner product. This object here is a 4D bulk operator, the one that I talked about before. And then I take the inner product with a spin S conformal primary wave function with boost weight and spin, which depends on a bulk point and on a boundary point. These inner products often have a complex conjugation going on, so that's the star here. And what this inner product here actually denotes is some spin S inner product which essentially corresponds to an integral over some Cauchy slice. So and now let me translate this into terms that you might be more familiar with. So let's do this for a scalar. So what does this mean for a scalar? So for a scalar, this object OS, so S equals 0, which depends on X, I would write down a mode expansion. So let me say proportional to D3, some dummy variable, some dummy momentum variable K. K0, I'm dropping the 2 pi's here and other factors of, let me drop just the 2 pi cubed. There's a creation operator that depends on this momentum, dummy variable e to the ik dot x plus the Hermitian conjugate. So that's your mode decomposition. And the spin 0 conformal primary wave function is proportional just to, in the momentum basis, let me do it that way, to the e to the ip dot x. So e to the plus minus I omega q dot x. And so if I work in the energy basis, this object here would not give me something with a boost weight, but with something that has an energy. So let me do that first. So using this definition, but with all the objects having energies, this would give me a 2-dimensional operator labeled by its energy. So I use the same definition, but replace the deltas by omegas. And how do I get that? Well, for scalars, the natural inner product that I would be looking at here is the Klein-Gordon inner product, right? You've seen this? Klein-Gordon inner product. So if you do that, you compute the inner product of this bulk operator with a wave function. And you should have learned in your QFD course that there's some orthogonality relation for inner products of plane waves, right? So they're either 1 or 0 depending on whether you stick a plus or minus in there. So let me maybe make a side comment. So this is the object that the above will compute, and we will use that e to the plus minus ip dot x in the inner product with e to the plus minus I p prime dot x is a Dirac delta. So it's either, okay, I'm putting the 2 pi's back in here apparently. So e to the I p dot x with e to the I p dot p prime dot x gives a Dirac delta in the 3 momenta pi minus p prime I, okay? So when you plug in a plane wave in here with this mode expansion, you will have inner products between this plane wave and that plane wave and this plane wave and that plane wave. One of them will be 0, one of them will be 1. And the one that gives 1 will tell you that whatever is the coefficient of this plane wave, so these correlation annihilation operators, is the operator that you get on the left-hand side. Okay? So if you do this in the energy basis, you expand it in plane waves, you take here as your wave function a plane wave, you use the orthogonality between plane waves, you then either get A or A dagger. And this will give you what I call the operator and the energy basis. So it's either A or A dagger, which depends on omega and the point on the sphere. Now I can do the same thing, but instead of plugging in plane waves, I plug in these conformal primary wave functions. And then instead of getting O omegas, I will get O deltas. And they will now be creation or annihilation operators for particles with definite delta rather than omega. Okay? So this is a fancy way of defining the boundary operator. All that I'm saying is that you get either the A or an A dagger, maybe dressed with some factors and normalization and so on, but you get A or A dagger with dependence on delta rather than omega. Okay? Is that clear? So we want to talk about asymptotic states. We have written down the wave functions that make Lorentz symmetry manifest, and now we have introduced 2D operators that also make Lorentz symmetry manifest. So we could sort of write down that we have an object that has a state that has dimension delta, j, z, and z bar. And we may think of it being created by an operator with dimension delta spin j, inserted at a point z, z bar, acting on some suitably defined vacuum. And then there is a plus or minus label that I should also put in here. Yes?
The final part of the right-hand side is saying that if we use instead the meta transform file,
Yeah.
we're going to get all that.
Yes.
But can I do a meta transform on this whole omega and get the same?
Yeah. It just says, so this is the long-winded way of saying that you take A of k, write it in terms of like the omega in there and the x, and you Mellin transform it, and then that omega will go away and that A will get a delta label. That's the short version of saying what I said here. Okay. All right, so now we talked a lot about doing the Mellin transform, and let me just remind you that we started out with some objects, let me talk about states here now, that have energy omega, helicity L, which is given by plus or minus the spin S. And we also discussed when L can be smaller than the absolute value of S. And then we have like X, which is little x, which is Z bar. I think I'm switching from capital A to small a from the rest of the lecture because this is what we do in the literature, but never mind. So we talked about doing this Mellin transform here to go to something that has, so we had energy here, helicity here. Now we get boost weight here. Now we call this 2D spin. The x remains untouched. So this would be the asymptotic state. But we can also go backwards. So we can do an inverse Mellin transform to go backwards. That should be in delta. It will have omega to the minus delta. And we're going to sprinkle some factors of 2 by I here. And it turns out if you do an inverse Mellin transform, the range over which you should integrate is from 1 minus I infinity to 1 plus I infinity in 2 dimensions. And now you wonder, well, why is that? And what is even delta? We haven't even talked about the range of delta, so let's do that now. Okay. So let's talk about the energy basis. So what kind of different omegas do we have? Well, we can look at omega bigger than 0. Okay, that's the usual thing. But then we learned yesterday that we can also look at the limit where we take the energy to 0. Okay? And we saw that, well, this has a name. It's the soft limit. And let me put here the word energetically, because it's soft in energy. And we saw that this, if you take omega towards 0, then if you apply this to scattering amplitudes, then we get an expansion that starts with 1 over omega, omega to the 0, omega to the 1, and so on. Now, what do these two distinct cases map onto in the Mellin basis? In the conformal basis, the boost basis, celestial basis, you can say all these words, they all mean that thing. So what that means is if you look at, let's say, again, plane waves with some finite energy omega, what does that map to? So how do we figure out what kind of basis of states we can have in the energy basis? So we said we like plane waves. Unfortunately, plane waves form a delta function normalizable basis, right? So there's this orthogonality relation that I just talked about, and so plane waves form a basis. If we Mellin transform the basis, we should get another basis, right? But this basis was in terms of omega, and now we get rid of omega, we get delta, so this basis needs to be something in terms of delta. So it turns out if you look at the inner product of plane waves and you take the Mellin transform and you want again to have something that is a delta function normalizable basis, a good range for delta is when it is given by 1 plus I times some real number. And if you are not in 2 dimensions on the sphere, but in d dimensions, then this number is d over 2. And we have been looking at d equals 2 for now. And this range of delta has a name. It is called the principal series of the Lorentz group, principal continuous series of the Lorentz group. And this gives you unitary representations. So even though there's an I in here and looks complex, and you might think, well, this is weird, non-unitary, whatever, it gives you unitary representations of the Lorentz group. Principal continuous. So, okay. I mean, you see it's continuous. Sorry? There's a discrete series, and then there is a principal continuous series. There's exceptional series. There's all these things. Here, finite energy wave functions map naturally onto wave functions on the principal continuous series of the Lorentz group, which just means you take the delta to be a specific complex value whose real part is determined by the dimension that you're in. Okay, so that's that. What about this energy 0 case? What about this energetically soft case? We integrate over energy. Does the soft limit now disappear? We don't have a notion about soft anymore, energetically soft. What does it become? So it turns out that this case actually maps to a specific, so here we have this expansion, and every term in this expansion maps to specific values of delta. So these values, let me say roughly first, that omega to 0 maps to integer values of delta. This kind of smells like a discrete series. And now this energetically soft limit becomes what we called conformally soft limit. In the simplest case, this means that so you can write the conformal dimension as a left and right conformal weight, h and h bar. And in the simplest case, for the photon, it means that one of these is 0, So that's why we gave it this name. But then more generally, for other spinning particles and for each value in this expansion, you get an object that has a specific value of delta that may not be 0. And so what we will find is that when we take an amplitude and we take the energetically soft limit, and we get as a leading term this, as a subleading term this, and so on and so forth, like the leadings of graviton, the subleadings of graviton, and so on. If we Mellin transform our entire amplitude, and I forgot to tell you, this is what we call celestial amplitude. So S matrix in the Puhm spaces, we call celestial amplitude. If you do that, and you take instead of, before you took the energetically soft limit, you get this expansion. If you Mellin transform and you take specific values, you go towards specific values of delta, you can extract the coefficients of these terms in the expansion. And they will be the coefficients of certain poles in delta that are at integer values. So the 1 over omega pole will map to a pole in 1 over delta minus 1. The omega to the 0 term will map to a pole in 1 over delta at 0. Okay, let me write this out, minus 0. The omega to the 1 term that we haven't really talked about, but you could look at that too, maps to a pole in delta minus 1, and so on. Okay, and you can easily see that by just doing the Mellin transform of these terms here. So let's say we go from, since we're looking at the soft limit, all that we care about is going on in the deep IR. So let me put some omega cutoff there. And then let me write the Mellin transform as d omega over omega. Then I have omega to the delta. And then I have special powers here. So let me call these special powers delta S, which would be minus 1, 0, 1, and so on. And the result of this integral is, well, something in terms of this cutoff. And then there is a pole delta minus delta S. You just do this integral, you get a pole, and this delta S corresponds precisely to these values here. Okay? So this is how the soft limit, the energetically soft limit gets mapped to in the celestial Puhm spaces. Okay. Okay, so now we can get back to these special soft theorems that we talked about yesterday. And I want to sort of end on showing you that there's a stress tensor appearing in the celestial conformal field theory. Okay. Are there any questions? Okay, so we have now seen that these terms in the expansion get mapped to these simple poles at special values of delta. Now let's look at what this means for the soft photon theorem, the soft graviton theorem at leading and subleading order. Okay? Just let me write this down again to let it sink in. So the soft factors in an energetically soft expansion map to simple poles in mostly negative. So the first two is not negative, but then all the rest are negative in the Boost weights. So let's look at photons. So we wrote down yesterday how the soft photon theorem looks in this basis where we took a special form of the momenta in terms of energy and point on the sphere. And then we saw that they kind of looked like a correlation function of a U1 current. So let me now take my original soft theorem and let me apply to it this Mellin transform. Yeah? So, and let me denote, let me do this here. So my energetically soft momentum amplitude, I denoted by n. or n plus 1 for the one with the soft particle. Under the Mellin transform, it maps to a celestial amplitude, and just for notation, let me call this m. So my Mellin transformed amplitude, I will call m. So we have an n plus 1 point amplitude, celestial amplitude, which instead of depending on the energies, now depends on the deltas. That one here has dimension delta and spin j. And then I have boost weights and spins for all the other n particles. So I'm not going to write them out, but there's delta i's and j i's for each of those n hard particles in the scattering process. And we found yesterday that in the energy basis, this looked like something charges, qi of the hard particles, divided by z minus zi, where z is the location of the particles on the celestial sphere, and z is the location of this soft particle. And this was multiplying the n-point amplitude in hard particles. So you see that structure almost carries over. But what I haven't written here is this pole in the energy. So in a energy momentum basis, I have this pole. I told you now that when you do the Mellin transform, this maps to a pole. So I should write this pole on the right-hand side. But I don't like so much objects that blow up, so I will multiply this on the left-hand side, delta minus 1. And what this tells me is that this polarizes when delta goes to 1. So I take this limit, delta to 1. And that's the same delta as, that's the delta of this soft particle. Okay? And then we saw yesterday that, well, the right-hand side looks like what you have on the right-hand side of a current correlator. So there's a J, and then these n particles are some operators, delta I, Ji from 1 to n. Okay? And this J here is precisely the object that has dimension 1 and spin plus 1. Or I can write this in terms of h and h bar, which are just 1/2 delta plus j, delta minus j. And so this is 1, 0. And so this 0 is kind of the name why we called it conformally soft photon. I might put a z here to just denote that this is the plus helicity. Okay? And so what this object is, so this J here is a conserved current in celestial conformal field theory. So that, very good. So thank you for asking. This was my next point. So yesterday we said in the momentum basis, this already looks like a correlator of a current. Now I have Mellin transformed this to the celestial amplitude. And what defines my current now is the conformal primary operator that denotes this n plus 1th particle together with this prefactor. So that one here, when you Mellin transform, this will correspond to some operator O delta J. If you multiply this operator of definite spin and boost weight by delta minus 1 and take this limit, this is what I call J. Okay? So yesterday, this role was played by the particle in here that had omega equals 0, and then there was a 1 over omega pole on the right-hand side. Now this 1 over omega pole becomes this delta minus 1, and after the Mellin transform, this operator O omega becomes operator O delta, and if I multiply it by this and take the limit, I get something that I call a conformally soft operator. The one that has dimension 1 and spin plus 1 will be a holomorphic current J. Okay, and now to finish up here, let's look at gravity. So these are the last two things that I write down. So gravitons. So I'm going to do the same thing here. I'm going to just write down what we had yesterday, and I will Mellin transform that object. So here, this object that I chose had spin 1. Now this object that I choose has spin 2. So this is part of the structure that we had yesterday. Now, because I'm again talking about the 1 over omega pole, but not for gravitons, again, I multiply this delta minus 1 over, take the limit. Then we said, well, the right-hand side doesn't look like anything that we're familiar with in CFD. So let's try to make this into something that looks familiar. So you take a z bar derivative, then this goes away, and we have z minus zi here. And let me already write this celestial amplitude as a correlation function. On the right-hand side, I also get a correlation function. There's some O delta I ji. And now I have to put some name here. So again, I call this together with this n plus 1th particle of dimension delta and spin plus 2 something. So this is something that arose after taking a derivative. And then it gives me something that looks like a current correlator. So let me call it PZ. And you can convince yourself that this operator, so the one that we started with, had dimension 1, so that's the limit that we're taking, and spin plus 2. You can convince yourself that after you take a z bar derivative, that this object will have dimension and spin 2, 1. And because we have taken this derivative here, this operator is actually not a primary. What is it when I take a derivative of a descendant? Oh. Good. Okay, this is a descendant. Very good. Okay. And what else do I want to say here? Something very important, which I omitted here. So in the energy momentum basis, we had a factor of omega I here, if you remember. We said this doesn't look really like, even if you put it here, this doesn't really look like a current because we have this omega dependence here. Now we have removed that omega dependence because we have taken the Mellin transform. So this omega has to come somehow into these delta i's here. And actually, what should be written on the right-hand side here is not O delta I ji, but O delta I plus 1. And this is because of this extra factor of omega I, which becomes something in delta I. So each extra factor of omega that you put in here will go as an additive thing in this exponent. Okay, so whatever your delta was gets shifted by however many extra factors of omega you have. And so this is how translation symmetry arises in the conformal primary basis. Translations are generated by the momentum operator. The momentum operator has a factor of the energy. Now you Mellin transform that. Factors of energies become shifts in the boost weight. Okay? And I'm sorry for going over time. This is really the last thing that I'm writing down here. To close the circle. So for the subleadings of graviton theorem, we can also write down a corresponding correlation function. We had it yesterday, so let me just write it out. So yesterday we had written omega I d omega I plus Li over z minus zi squared minus d by dzi over z minus zi. That thing acts on the remaining endpoint amplitude, which is a correlation function in a conformal basis, delta I ji. And then on the right-hand side, so now we're talking about, sorry, I erased it. We're talking about not the 1 over omega pole, but the constant term. And that constant term is a pole at delta equals 0. So I just multiply the left-hand side by delta and take delta to 0. And what I will have on the right-hand side is another correlation function. But now the operator so there's an operator delta J, spin plus 2, let's say, plus 2. And this here, the limit of, okay, actually, I have to say something else here. Okay, so this is because I have no time left. So if you take the sublimits of graviton theorem and you Mellin transform it, you get an operator that has dimension 0. But we talked yesterday that whatever you get on the right-hand side didn't look like something familiar, and I told you that you have to do some smearing on the celestial sphere to make it look like something familiar. So that smearing in CFD is called a shadow transform. It's a specific transform that you do. And when you shadow transform the right-hand side of the sublimits of graviton theorem, you land on this object. But what a shadow transform does to an operator of dimension delta is it takes it to another operator of dimension with shifted delta. In 2 dimensions, this means delta goes to 2 minus delta. And so the operator on the left-hand side will not be an operator where the limit is taking delta to 0, but the limit is taking delta to 2. And now you see where I'm going with this. The right-hand side, what does it look like? Correlation function for what operator in CFD? Somebody says it, I hear it. If you just if you replace this by some number, what does this look like? Stress tensor, yes. So in the momentum basis, we wrote this, but now we got rid of the omegas. So all these omegas become numbers, no longer operators. And these numbers turn out to be just the conformal weights of the operators here. So this H is HI plus H bar I. And then the operator on the left-hand side is nothing but the stress tensor, the holomorphic stress tensor. So this is how a 2-dimensional stress tensor arises for celestial conformal field theory. You take the subleadings of graviton theorem, you Mellin transform it, you realize that you have to do some smearing to bring it to some nice form. The smearing is the shadow transform. After you have done that, you have gotten really a correlator where this is a number, and you can identify this operator on the left-hand side with the stress tensor of dimension 2. And so this is one of the big motivations that there should indeed be a celestial conformal field theory living on a 2-dimensional sphere, which should capture some bulk physics. And in particular, the stress tensor correlation function captures the subleadings of graviton theorem in the bulk. And because it's the stress tensor, it enhances global conformal symmetry to local conformal symmetry. And this provides sort of the bedrock motivation for why we expect there to be some kind of conformal field theory on the celestial sphere. Okay, questions? Yes? Delta equals, this one? Yeah. So the object that you start with here after your Mellin transform is an object that has dimension 1, because we took this limit, and spin 2. You can write this in terms of H and H bars. And what you learn in 2D CFD is when you take, so you can take derivatives with respect to Z or derivatives with respect to Z bar, and they will increase the value of delta as you go down. So this is why we went from delta to 1 to delta to 2. And depending on whether you choose Z and Z or Z bar derivatives, they will, yeah, exactly. They will, in this case, decrease the spin from 2 to 1. Yeah. If you take dz, so if we started with the -2 object instead of the +2, I would get the other one. Yeah, then exactly. Because then the Z bar and Zs would be flipped here, and in order to get to something that looks like a current correlator, I would have to do the other one, yeah. Yes, sorry for going over time.